In this video, we're going to look at another example of finding radius and interval of convergence of a power series. This one's going to have a little bit more general terms to it. Will be centered at A and have some constant B raised to the nth power, where we know we have a positive constant B so that the terms are not alternating. All right, so let's attack this using the ratio test. Root test probably isn't going to be very easy for us in this case because of this natural log of n term with no power on it. So again, ratio test involves limits of consecutive terms. And then we'll put the pieces together that match each other. We have a natural log of n that'll come up to the top over the natural log of n plus 1. Actually, this series should start at 2, not 1. That's a typo. This should start at 2 because I can't plug 1 in for natural log of n. So anyway, let's just suppose this starts at 2 so we don't have any issues with convergence, which is not important here as far as we're concerned with what we're doing because we're going off to infinity. But we'll have natural log of n over natural log of n plus 1. Those are all positive, so we don't need to worry about the absolute value bars. We've got a b to the n plus 1 will be on top and a b to the n on bottom. So we've got that piece there. That'll simplify to a b. We're told that b is positive, so I don't need to worry about absolute value bars there. X minus a to the n plus 1 over x minus a to the n. We'll simplify it as just an x minus a. And since values for x could be positive or, less than a or bigger than a, this certainly will still need the absolute value of bars around it. All right, this simplifies to b. This has no n's in it, so that part will just be in the limit because I don't have to worry about the n's. Natural log of n over natural log of n plus 1 goes to 1 as n goes to infinity. L'Hopital's rule is probably one of the easier ways to check that if you need to check that that really does go to 1. Ratio test says that we need this limit to be less than 1 in order for the power series to converge. Solving for the absolute value piece, we need absolute value of x minus a to be less than 1 over b. So the radius of convergence in this case must be 1 over b. This power series is centered at a. The radius is 1 over b, so our endpoints must be a plus or minus 1 over b. We have to go to the left 1 over b and to the right 1 over b from the center. When we have x is equal to a minus 1 over b, plugging that in for x, here we subtract the a off the a minus 1 over b, so we're just left with negative 1 over b to the n. Your b to the n's will cancel, so we're just left with negative 1 to the n over n. This is an alternating series, and the terms are going to 0, and they decrease, so it'll converge by the alternating series test. Again, remember that this is a typo. These should be starting at 2, not 1. And these two as well. When x is equal to a plus 1 over b, this whole thing will simplify to just 1 over natural log of n. The alternating piece is not there in that case. This will diverge because natural log of n is less than n. So when we reciprocate, 1 over natural log of n will be greater than 1 over n. We know that the sum from the 1 over n's diverges. This is the harmonic series. So this one must also diverge because it's bigger. So then our interval of convergence goes from the a minus 1 over b included to a plus 1 over b excluded.